Before 2017, the common wisdom for sequence tasks like translation relied on recurrent or convolutional networks. They were effective but had a bottleneck.
That's right. The way RNNs process words one after another always felt like a sequential assembly line, which made them hard to speed up.
Exactly. The authors here note that the dominant sequence transduction models are based on complex recurrent or convolutional neural networks. It was the standard.
And the complex part feels right. They often involved intricate gates or layers, making them challenging to design and optimize.
This paper also says the best performing models also connect the encoder and decoder through an attention mechanism. We've talked about attention before as a way to focus.
Yes, in case number TCM 063003, we saw how attention helps models like BERT understand context bidirectionally. It was a crucial helper for RNNs and CNNs.
But the groundbreaking leap here was to say, what if attention isn't just a helper? What if we could propose a new simple network architecture, the transformer, based solely on attention mechanisms?
So no RNNs, no CNNs, just attention. That sounds incredibly bold. It's like saying, let's take away all the scaffolding and see if this one core piece can stand alone. This analogy works because, like scaffolding, RNNs and CNNs were seen as structural necessities. But unlike physical scaffolding, the core piece of attention needed new layers to handle sequence order and locality, which the original scaffolding provided.
It was. And the key was dispensing with recurrence and convolutions entirely. This wasn't an incremental improvement, it was a fundamental architectural shift.
I can imagine the skepticism at the time. Recurrence felt essential for sequences. What did they gain by throwing it out?
The main gain was efficiency. They found these models to be more parallelizable and requiring significantly less time to train. This improvement in parallelization was critical for scaling models to large datasets, significantly reducing training times.
Parallelization directly addresses my assembly line problem with RNNs. If each word's context can be built simultaneously, that's a massive speedup.
Not only faster, but better. It achieves 28.4 BLU on the WMT 2014 English to German translation task, improving significantly over prior state-of-the-art models.
So it wasn't just theoretical. It delivered concrete, superior results on real-world tasks like machine translation. That's a strong argument for the new architecture.
This paper lays the groundwork for understanding why the transformer became so dominant. Now, let's get an intuitive grasp of how this attention-only model actually builds understanding.
I'm ready. How can solely attention perform so well? I still need to see the pieces.
This illustrated guide highlights that the transformer is a model that uses attention to boost the speed with which these models can be trained.
So the speed comes from how it uses attention. But how does it handle sequences without recurrence? That's the part I'm curious about.
At a high level, it still uses the familiar an encoding component, a decoding component structure that many sequence-to-sequence models employ.
Okay, that's a familiar pattern from previous models. Encode the input, then decode to produce the output. So the overall goal is the same, just the internal machinery is different.
Each of those components is a stack of encoders or decoders. Each encoder processes the input, refines it, and passes it up to the next layer.
So it's like a multi-story building where each floor processes the information from the floor below, getting more abstract or refined at each step. This building analogy is helpful for visualizing depth.
However, unlike a literal building where floors are physically distinct, these encoder layers don't necessarily operate on entirely separate data streams. They are processing the same information, just at different levels of abstraction.
Now, you might be wondering, if we got rid of recurrence, how does the transformer know about word order? That's where positional encodings, to inject some information about the relative or absolute position of the tokens in the sequence, come in.
So this is how it handles the sequence order and locality that I mentioned earlier. Instead of processing sequentially, it bakes the position information directly into the input embeddings before any attention happens.
The core of each encoder is a self-attention layer, a layer that helps the encoder look at other words in the input sentence as it encodes a specific word.
Self-attention. We've encountered attention helping an output word look at input words, but self-attention means looking at other words within the same input sentence?
Precisely. The guide gives this example. The animal didn't cross the street because it was too tired. What does it refer to here?
A human knows it is the animal, not the street. But for a computer, that's a difficult contextual challenge without a mechanism to associate words.
Self-attention is that mechanism. It allows it to associate it with animal. For each word, it generates an enriched representation based on all other words.
So it's like a dynamic highlighter. When processing it highlights animal and uses that information to make the representation of it more accurate. This highlighter metaphor captures the selective focus. What it doesn't convey is that this highlighting isn't just a visual aid, it's a mathematical operation that literally reweights contributions from all other words to form a new context-rich representation.
You can think of it like this. If you're familiar with RNNs, think of how maintaining a hidden state allows an RNN to incorporate its representation. But self-attention does it in parallel.
So an RNN builds context sequentially, word by word, updating a single state. Self-attention builds a context for each word by looking at all other words at once.
Now that we have this intuition for self-attention, let's dive into the core technical mechanism. How exactly does it look at and associate words?
I'm ready for the math. How do we turn highlighting into an actual calculation that generates a new vector?
The first step in self-attention is to create 3 vectors from each of the encoder's input vectors. These are called query, key, and value vectors.
3 vectors for every word? So if I have a 10-word sentence, I'll end up with 30 vectors. How are they created?
Exactly. They're created by multiplying the embedding by 3 matrices that we trained during the training process. These matrices project each word's embedding into Q, K, and V spaces.
So the model learns how to generate these query, key, and value representations. It's not a fixed calculation, but a trainable projection.
The guide asks, what are the query, key, and value vectors? Think of a query as what I'm looking for. This is a good mental anchor. More precisely, a query is a vector representing the search criteria for the current word's context.
Exactly. The keys are vector representations of the information contained in each word, used to match against the query. The analogy to searching is strong, as the dot product quantifies this match.
That's a great intuition. The next step is to take the dot product of the query vector with the key vector for each word in the sequence.
Dot product measures similarity. So for the word it, its query vector is compared with the key vector of animal, street, tired, and so on.
Those dot product scores are then divided by 8, the square root of the key vector dimension. This is a scaling factor to stabilize gradients.
And then after scaling, they're past the risk softmax. That will give us a probability distribution, right?
Precisely. As the text states, softmax normalizes the scores so they're all positive and add up to 1. These are now our attention weights.
So these weights tell us how much attention or focus each other word should get when we're encoding the current word.
The final step for each position is to multiply each value vector by the softmax score. This weights the values according to their relevance.
And then sum them up? So the output vector for 8 would be a weighted average of all the value actors where the weights come from its query matching other keys.
Exactly. You sum up the weighted value vectors. This output vector effectively bakes in the context. The crucial point is, this can happen for all words in parallel.
That's the parallelization. Each word computes its QKV, then its attention weights and its weighted sums simultaneously. No sequential dependency like an RNN.
What we've described is single-head attention, but the transformer uses multi-head attention, allows the model to jointly attend to information from different representation subspaces at different positions.
So instead of just one QVK set for each word, we have several. Each head learns to focus on different types of relationships or contexts. Like one head might focus on grammatical dependencies, another on semantic similarity.
Precisely. The outputs from these multiple attention heads are then concatenated and linearly transformed. After this, the outputs of the self-attention layer are fed to a feed-forward neural network.
So after self-attention gathers contextual information, a standard neural network layer processes that refined information independently for each position. It's like a final pass to integrate the attention output.
And for stability and deeper learning, each of the 2 sublayers in each encoder, self-attention and FFN, has a residual connection around it, followed by layer normalization.
Residual connections help with training deep networks by allowing gradients to flow more easily, and layer normalization helps stabilize activations. So these are crucial engineering details that make the deep stack of encoders actually work.
Despite all its advantages, self-attention isn't without its limitations. For an input sequence of length n, it has a single attention layer with O of n squared d complexity, meaning the computational cost grows quadratically with sequence length. Quadratic?
That sounds like a big problem for very long sequences, like entire books or high-resolution images. Does that mean there's a practical limit to how much context it can efficiently process?
It does, but solutions like sparse attention or breaking inputs into smaller chunks are actively researched. However, for most NLP tasks, the parallelization benefits still make it more parallelizable and requiring significantly less time to train compared to RNNs.
So it's not a silver bullet, but its strengths outweigh its weaknesses for a broad range of applications, even with ongoing research to tackle its quadratic complexity.
This self-attention mechanism, repeated in layers, allowed transformers to become the leading architecture in NLP. What's also significant is how this same idea successfully generalized to other domains.
I'm thinking about our previous cases on transformer generalization. How does this language model make sense of something like images?
For a long time, even after transformers revolutionized NLP, their applications to computer vision remain limited. Convolutional neural networks, or CNNs, were the reigning champions for image tasks.
Right. CNNs just seemed inherently suited to images, with their ability to capture local features and build hierarchical representations. How could an attention-only model, designed for sequences of words, possibly compete?
The core innovation was to apply the same tokenization principle. Instead of turning each input word into a vector using an embedding algorithm, they adapted this by splitting images into fixed-size patches.
So, each image patch effectively becomes a word or a token in a sequence. It's the same tokenization idea we saw in NLP, but now it's breaking down visual information.
Just like with language, these image patch embeddings need to know where they are. So for images too, we use positional encodings to inject some information about the relative or absolute position of the tokens in the sequence to preserve spatial information.
That makes sense. Without positional encoding, the transformer would see a shuffled bag of patches, losing all the spatial relationships crucial for understanding an image.
These patched inputs, along with a special class token for classification, similar to BERT's CLS token, are then fed into a standard transformer encoder. It connects all positions with a constant number of sequentially executed operations internally, just as we discussed for text.
So the same self-attention layers process the relationships between image patches, effectively learning how different parts of the image interact to form objects or scenes. It's literally the same architecture, just with a different input.
And the results were astounding. This pure transformer model, the vision transformer, proved that the transformer generalizes well to other tasks, achieving state-of-the-art performance on major image recognition benchmarks, often surpassing CNNs.
It's incredible that a model designed for text could achieve state-of-the-art in vision just by reframing the input. It truly highlights the generality of the attention mechanism and parallel processing across modalities.
It validated the paper's bold claim. The transformer, based solely on attention mechanisms, dispensing with recurrence and convolutions entirely, could be a universal learner for diverse data types, not just text.
From translating languages to recognizing objects, all with just attention. It's a paradigm shift, proving that the all you need in the original paper's title wasn't an exaggeration. It was a prophecy.